Hello. Now we are going to look at quadratic sequences or quadratic patterns. A quadratic is something that it has a highest power of 2. So if we look at the general form of a quadratic, this is the same in functions, in normal algebra, as it is in sequences. This is what a quadratic function or a quadratic pattern looks like in general. We have the highest power squared, and then we often have a linear term. We have n to the 1, and then we have a constant, just a number on the end. So this is a quadratic trinomial is another way we could have described this. And again, it's the general form of quadratic, and we have to know that by heart. Now there's some facts about this formula that we have to just quickly discuss. The second difference of a quadratic is always constant. Just like when we had our linear patterns, and the first difference, the difference between each one of the terms, was constant. It was the same every time. That's what gave us a linear pattern. Well, this time, the second difference, or the difference of the differences, is going to be constant. We're going to look at that in practice in a minute, but that's the core defining thing that tells us if we've got a quadratic pattern. Is the difference of the differences a constant? And another fact that we just have to learn off by heart for now is that the second difference, the difference of the differences, is equal to twice the a that is in our formula here. So a is the coefficient of the n squared term, the first thing that we come across in our formula. And unhelpfully, we already have a meaning for a in patterns, but you are going to see it meaning something different for a quadratic pattern. The a that we're used to for a linear pattern was our first term. A was equal to tn, or t1 I should say, from our log tables formula. A does not mean the same thing here. A is the coefficient of the n squared term. It does not mean the first term in our pattern. So we need to be careful of that. Even though it's the same letter, it's in a different context, it's being used in a different way, and a is just going to be the coefficient of our n squared term. And we have to know, as a rule for helping us solve certain problems, that the second difference is equal to twice this coefficient. So let's have a look at doing this in practice. If we have a quadratic like this, how would we get our t1, our t2, our t3, our t4? So we would have our pattern here doesn't actually have an n term, it just has an n squared term and then a constant on the end. And that's okay, that's still a quadratic. This is the general form, but so long as we've got a squared thing as our highest power, then it's a quadratic. So let's put in n as 1 for t1. And we end up with 1 minus 2 is going to be minus 1. And then 2 squared minus 2. We end up with 4 minus 2 is going to be 2. And 3 squared minus 2 is going to be 9 minus 2 is going to be 7. And 4 squared minus 2 is going to be 16 minus 2 is going to be 14. Now, so we've used this formula here to generate the numbers in our list, to generate the terms in our pattern. So we know this is a quadratic pattern because we saw the formula, the rule that gave us the list, but we know that the second difference must be constant for a quadratic. So this isn't particularly required in a normal question, but just to highlight what's going on with a quadratic pattern. What's the difference here? Well, the difference here is we add 3. The difference here is we add 5. The difference here is that we add 7. Now, here we can see this is not a linear pattern because we're not adding the same thing each time. So this is D1. This is the first difference, the difference between the terms. But we now know for a quadratic pattern that the second difference, that is the difference of the differences, must be the same each time. And we can see here that it is. A difference of the differences, the difference is going up by 2 each time. So it is increasing by 2 each time. That means the second difference is constant. It's just plus 2. And again, we would know that D2 would be equal to 2a. So equal to 2 is equal to 2a. So we know that a is equal to 1. And we can see that in the formula. The coefficient of the e squared term is 1. So we'd have 1n squared. So that is what we've got for our introduction to a quadratic pattern. Now, if we were asked to find this, to find the nth term or the general term for this pattern, how would we do it? Well, to begin with, we have to be sure that we've got a quadratic pattern. How do we do that? We have to check that the second difference is constant. So what's our difference between our terms here? Because in an exam, we could be given a linear pattern. So here we're adding 4, here we're adding 10, here we're adding 14, here we're adding 18. So we don't have a linear pattern. So we check, our next thing to check is, have we got a quadratic pattern where we're adding 6 and we're adding, not adding 4 there. We're adding 6 here. My apologies. So correction in here, if we're going from -1 to 5, we are adding 6. So we're not adding on. If we have a look at our differences now, we're going from 6 to 10. So our difference is changing by 4 and by 4. And again, we're adding on 4. So that was our first difference, and it was changing all the time. And then our second difference, we can see we're adding 4 each time. So our difference is getting bigger by 4 each time. So our second difference is constant, and it's just equal to plus 4. Now we know that the nth term for a quadratic pattern looks in general like this. And now what we have to do for a particular pattern is to find the value of a, b, and c. And if we knew the values of a, b, and c, then we'd have a formula like this that would give us all of the numbers, all of the terms in our pattern. So what we've got to do now is find our values for a, b, and c. Well, we know a rule for a. We know that the second difference is equal to 2a. And we know that the second difference is plus 4. So 4 is equal to 2a. So divide both sides by 2 to get a by itself. So a is equal to 2. So long as we can remember that, we have a fairly quick start to our question. We know that our value for a is 2, so this is what our pattern looks like. But we still need to find b and c. So how are we going to do that? Well, we're going to use simultaneous equations. And the way that we're going to do it is, we know that this pattern should give us all of the terms in this list. So what does that mean? Well, it means when n is 1, our pattern should be equal to -1. Our formula, I should say, should be equal to -1. We put in 1 for our value for n. We know term 1 in our pattern must be -1. So that means that 2 plus b plus c must be equal to -1. Rearranging this to get b and c by themselves. So that gives us an equation in b and c, but we don't have b and c just by themselves, so we need to go again, and term 2 must be 5. We know that this formula must give us 5. We have 2 on 2 squared plus b on 2 plus c is equal to 5. The second term in our quadratic pattern must be 5. So we multiply that out and we get 8 plus 2b plus c is equal to 5. Rearrange to get the letters on one side and the numbers on the other. So we have 2b plus c must be equal to -3. Now we could keep doing this, but we don't actually need to, because we know for our simultaneous equations, we have 2 equations and 2 unknowns. So we're sorted. We have equation 1 and we have equation 2. And now we need to add up these equations so that one of the letters sums to 0, so that we get an equation that has only one unknown in it. So let's take equation 2. So 2b plus c is equal to minus 3. And we're going to subtract equation 1 away from that. That's minus b minus c is equal to plus 3. So I can see then that if I add these two equations together now, so remember with our simultaneous equations we get the same number and a different sign in front of one of our letters. Well, we've got that. We have plus 1c and minus 1c now because we've subtracted away equation 1. And when we add these two equations together now, we're going to get rid of the c's and we'll have b, 2b minus b is just 1b. And then minus 3 plus 3 is 0. Now this might look like a problem, but it isn't. It just means that b is 0. The b in this formula is going to be 0. So it's going to be like this equation here. It's not going to have a n term in it. That's just going to be 0. So let's go back now knowing that and find the value of c. So b plus c is equal to minus 3. That was our equation 1. And we now know b is equal to 0. So 0 plus c is equal to minus 3. C is equal to minus 3. So now we can sub in to our pattern. And we have that a is 2, n squared, b is 0. So we can sub that in for now. Pardon. 0n. These in brackets. Plus c is minus 3. So tn is equal to 2n squared minus 3. The 0 multiplied by the n is just 0. So this is our formula for our quadratic pattern. So if we put in n is 1 into this formula, we should get minus 1. If we sub it in n is 2 into the formula, we should get 5. So let's just double check that. This is the job done, but let's just double check that our formula works the way we expect it to. And we can do this if we have time in an exam to make sure we haven't made any mistake. So we multiply that out and we get 2 minus 3 is minus 1. And t2, well, we should get 5. So let's see if we do. 2 on 2 squared minus 3. We would get 8 minus 3 is 5. So we can see that we are producing the numbers in our list. That's what our formula does. It gives us all of the terms in our list. So that is what we need for our quadratic sequences or quadratic patterns.